Originally put into service in the early 1950s, the B-52 stood as a key deterrent in the Strategic Air Command's arsenal. With its extensive range, the B-52 facilitated the global deployment of the Strategic Air Command's nuclear weapons. In contemporary times, the B-52 takes on roles such as low-level bombing and electronic warfare. While the Boeing B-52 represents the epitome of jet bomber design, its origins can be linked to a decision made by the Department of Defense a decade prior, during a period of national conflict. Throughout a significant portion of World War II, the United States prioritized the development of established technologies. This approach was aimed to facilitate the rapid production of essential wartime tools. Considerable advancements were made in piston engines during this period. The propulsion of every American aircraft engaged in intense aerial conflicts of World War II was driven by piston power plants. Even the formidable Boeing B-29, boasting superior speed, range, and payload compared to other bombers, relied on piston engine technology. While the B-29 was initially perceived as the pinnacle of aviation prowess, its technological supremacy was soon overshadowed by a new generation of aircraft. Early in the war, the United States was taken aback to discover that Germany and Britain had pioneered gas turbine jet engines, propelling fighters at speeds surpassing the legendary Superfortress. In 1944, the American Army Air Force issued a requirement for a jet bomber capable of outpacing jet fighters. Contracts were awarded for at least 5 distinct designs. However, it was the advent of nuclear fission that ultimately brought a swift and dramatic conclusion to the war. While the B-29 was utilized to transport the nuclear weapon, only one aircraft dropped one bomb, leading to the instantaneous disappearance of the city Hiroshima. The devastating capability of a single aircraft raises the possibility that extensive bomber fleets might no longer be necessary to secure victory in modern warfare. The significant human cost paid by America to establish B-29 bases in the Pacific altered the considerations for the next generation of bombers. In the early post-war era, strategic focus shifted towards the capability to deliver atomic bombs over exceptionally long distances, and the Air Force put its emphasis on long-range intercontinental aircraft, a role that Convair B-36 Peacemaker adequately filled for some time. The giant B-36 was really a Second World War design that arrived too late for combat. It required no less than 6 massive piston engines to propel it at what were average speeds. Later on, jet engines were incorporated in pods underneath the wing to augment its propulsion. By 1947, progress was evident in the jet bomber project. During that year, 5 submissions underwent testing, although they were categorized as medium bombers. Among the jets stemming from the 1944 requirement, the B-45 emerged as the first and second most successful. Its straightforward yet efficient 4-engine design was officially embraced by the United States Air Force and entered into service in a restricted quantity, primarily fulfilling reconnaissance duties. Consolidated proposed the B-46 as another 4-engine jet bomber. With its sleek lines, it stood out as one of the most aesthetically pleasing aircraft of its time, and its performance as an early jet was quite commendable. However, Consolidated's primary focus was on the B-36 production, and the medium bomber project did not receive high priority. Designed by Martin, the B-48 was a cumbersome aircraft with 6 jet engines arranged in mid-wing clusters. One notable feature was its bicycle undercarriage, positioned along the aircraft's centerline and supported by 2 outrigger wheels on each wing. Despite its innovative elements, the B-48 did not capture the interest of the Air Force, and like the B-46, the prototype was ultimately scrapped. In an effort to compete in the jet bomber program, Northrop took its existing piston engine flying wing and outfitted it with 8 turbojets. This wing design demonstrated exceptional efficiency and was notably ahead of its time. However, due to its unconventional nature, it struggled to secure government approval. Nevertheless, Northrop's mastery of flying wing technology eventually paid off 4 decades later, with the development of the B-2 stealth bomber. Today, the B-2's wing is a symbol of cutting-edge aviation design, but in 1947, the idea was considered far too revolutionary. Without doubt, the most impressive design offered to the Air Force came from Boeing. The design of the B-47 Stratojet by Boeing benefited significantly from the manufacturer's examination of German data regarding swept-wing technology. To maximize the efficiency offered by these wings, they were crafted to be extremely thin and flexible. Consequently, the 6 engines were suspended on pylons and distributed across each wing. This configuration not only facilitated engine servicing, but also provided aerodynamic advantages for the aircraft during high-speed flight. Due to the thinness of the wings, Boeing opted for the same fuselage-mounted bicycle undercarriage as seen in Martin's B-48. The Air Force adopted the B-47, leading to the production of hundreds during the early 1950s. It proved to be an exceptionally successful design, representing a classic example of having the right design at the opportune moment. Moreover, the B-47 served as an ideal testbed for Boeing to accumulate experience in producing efficient swept-wing jet bombers. One challenge with early jet engines was their relatively prolonged time to reach full power, particularly during takeoff. To counter the issue of prolonged engine power-up, Boeing implemented various iterations of detachable rocket boosters, pioneering what became known as Jet-Assisted Takeoff, or JATO. Following Boeing's renowned piston-engine bombers, the success of the Stratojet project solidified the company's standing with the Air Force for an extended period. The experience gained from the medium bomber project positioned Boeing favorably in the subsequent quest to develop a new long-range heavy bomber, aiming to replace the aging B-36 Peacemaker, an aircraft clearly at the end of its operational life. In a bid to prolong the Peacemaker's relevance, Convair introduced an all-jet swept-wing version designated the XB-60. However, retrofitting an aircraft originally designed during the Second World War failed to impress the Air Force. As early as 1946, Boeing had received a commission to devise a successor for the Peacemaker. The company explored a myriad of concepts, ranging from exceptionally large piston-engine aircraft to those featuring proposed compound supercharged power plants and others incorporating turboprops with jet engines driving propellers. But nothing provided the dramatic increase in performance over the B-36 that the Air Force was looking for. Recognizing the remarkable efficiency of the B-47's fully swept wing, Boeing proposed another all-jet design, loosely based on its medium bomber but significantly larger in scale. This concept evolved into the Model 464-67, and it was eventually embraced by the Air Force as the B-52. An order for 2 prototypes, the X and Y models, was issued in October 1948. However, due to minor issues with the X model, the YB-52 was completed first. The YB-52 underwent testing at Edwards Air Force Base. While its overall shape and fighter-like canopy resembled the B-47, its size and performance far exceeded it. The B-52 featured numerous advancements, including the all-steerable undercarriage that could align forward during landing, when even the aircraft veered to one side, a top-secret feature for several years. Apart from the cockpit layout, changed to a conventional side-by-side airliner arrangement, there were minimal external differences between the prototypes and the B-52s that entered production. Work began in earnest on the B-52A, now named the Stratofortress. Initially, only 3 B-52A models were constructed, but the B model, nearly identical to the B-52A with minor improvements, entered full-scale production. Enhancing the bomber's range was a consistent priority. In-flight refueling, perfected in the late 1940s using Boeing's flying boom method, addressed many challenges. However, during the early stages of the B-52 project, in-flight refueling posed difficulties. The early aerial tankers, powered by piston engines, had a maximum speed only slightly higher than the stalling speed of the jet bombers. In this image, the Y model grapples with the delicate task. The introduction of jet tanker refueling was clearly a safer and more preferable option. The advent of the KC-135 Stratotanker marked a significant turning point, making aerial refueling relatively safe and practical. Another approach to extend range involved incorporating extra-large outboard wing tanks, such as this example capable of holding 3,000 gallons, which could be jettisoned in combat situations. By March 1954, B-52s were rolling off Boeing's production line in Seattle. The planes then went into an induction program, where aircrew and aircraft were blended into one fighting machine. Inside this streamlined form, crews of 6 men mastered the intricacies of the Stratofortress. Compared to the B-36, Boeing's bomber was notably more confined. with every available inch allocated to fuel, payload, and electronics. While the B-36 boasted 6 gun positions, the B-52 had just 1. Instead of relying on multiple gun positions, the B-52 focused on performance and the emerging science of radar jamming for self-defense.
B-52 is a great plane because I liked flying it. It was a fun plane to fly. One of the most challenging things about it was refueling it. You get a plane that big, 500,000 pounds behind a tanker that's 350,000 pounds, and you got to transfer 120,000 pounds of fuel. That's part of the things that make it a great plane. It can go and go and go. I never got to fly it, but they used to fly 24-hour missions in B-52s, just refuel. So I think what makes a great plane where all the crews that flew it over so many years, my father was too old to fly, and I'm one of the younger people flying it myself, but there are probably 25 years older than flying it that are planes 10 years older than there.
The Strategic Air Command demanded the world's premier bomber, setting high standards for both its cutting-edge B-52 aircraft and their crews. Crew members underwent rigorous training, evolving into an elite corps of professionals, a team as adept as the sophisticated aircraft they operated. For over a decade, the Stratofortress and its crew held a singular responsibility, carrying and delivering thermonuclear hydrogen bombs. However, to serve as an effective deterrent, the bomb needed testing to validate its capabilities. Throughout the 1950s, hydrogen bombs were detonated in remote Pacific regions as part of these crucial tests. In the final tests, akin to many conducted earlier, B-52s were utilized to realize the formidable payloads. For the individuals involved, loading the most devastating device at that time conceived by human mind was a matter of precision and routine, a specialized task for the highly trained members of the Strategic Air Command team. Each cargo possessed a 100 megaton yield, a magnitude 100 times greater than the bombs dropped on Japan during World War II. In contrast to the weapons of that era, the device housed in this bomb bay would be decelerated in its descent from the B-52 by a parachute, affording the bomber more time to evacuate the area before the cataclysmic explosion. Driven by the concern of a potential Soviet atomic attack, the United States established an intricate network of detection facilities during the Cold War. Primarily located in the frozen north, the most probable route for a first strike, these early warning systems employed radar watchers constantly monitoring scanners scanning the sky for any blip. The Strategic Air Command maintained fleets of B-52s on operational standby, in a perpetual state of alert, poised to serve as the ultimate deterrent if the need arose. When the red phone rang, the procedure was automatic. Up to 100 Stratofortresses could be dispatched in a few short minutes. The routine was finally honed through regular exercises. The notion of an immediate retaliatory strike by the Strategic Air Command stood as the nation's best defense during the Cold War years. Entrusted solely to carefully screened officers, the task of nuclear deterrence fell upon the shoulders of nuclear-armed B-52 pilots, all holding at least the rank of major. They bore the weighty responsibility of commanding aircraft capable of altering or even terminating life on Earth. However, just as jets replaced piston engines, the B-52 and its high-flying Soviet counterparts were surpassed by a more efficient and lethal technology born in Nazi Germany. By the early 1960s, ground-to-air missiles had reached a level of perfection by both the US and the Soviets, making massive nuclear bombardment by aircraft challenging to achieve. The focus shifted to another delivery method: intercontinental ballistic missiles, or ICBMs. Years of development led to the creation of missiles like Polaris and Minuteman, eliminating the necessity for manned flights over enemy airspace to wage full-scale nuclear war. Despite this shift, SAC's Stratofortresses remained in service, as they still played a significant role in the precarious game of nuclear brinkmanship. The challenge with the ICBMs lay in their irreversible launch, denying politicians the time-honored tactic of saber-rattling and intensifying the risk of international conflict. The B-52, in conjunction with Hound Dog standoff bombs, presented a versatile alternative. Positioned at the very edge of enemy airspace, B-52s signaled America's preparedness to attack while allowing room for last-minute negotiations. The B-52's effectiveness was enhanced by the introduction of the quail decoy, which confounded enemy radar by replacing a Stratofortress's radio signal. Advancements after the Hound Dog led to the creation of the SRAM missile. Compact and deployable in greater numbers, the SRAM could be guided from within the B-52 to targets up to 100 miles away with remarkable precision. In 1965, the B-52 was employed for the first time in Vietnam. While now carrying conventional bombs instead of nuclear warheads, it retained its lethal nature. The wing mounts were equipped with 24 500-pound iron bombs, showcasing the adaptability of the aircraft in various mission profiles. The internal bomb load brought the total payload of each plane up to a total bomb load of 108. Throughout the Stratofortress's engagement in Southeast Asia, B-52s dropped over 3 million tons of bombs. While the use of these high-flying bombers stirred controversy at the time, there's little doubt about the Stratofortress's effectiveness in conventional bombing. Many historians contend that the extensive bombing of North Vietnam during the linebacker operations played a crucial role in compelling the enemy to return to the negotiating table, eventually leading to a ceasefire. In other Vietnam operations, more advanced bombs were employed. Some could be remotely detonated by personnel in other aircraft using infrared viewing equipment, synchronized with enemy activity. Standard 500 and 750-pound iron bombs were the norm for most B-52 raids. To expedite loading and turnaround, the internal bomb load was organized in pre-arranged racks, enabling swift installation. Crews stationed at Guam prepared for the lengthy 8-hour flight to the remote target. The crew in the front office and the solitary rear gunner assumed their positions as each aircraft readied for takeoff.
Well, the primary role of the B-52 in the Vietnam was basically tactical bombing of enemy troop concentrations. But it really started out, we used to cut roads early in '67. We did a lot of missions. We were interdicting trucks and supplies, but primarily we were cutting roads to back them up so the tactical forces could make the strikes. Later around Khe Sanh, we were really breaking up enemy troop formations. And we got very, very successful. As they had to concentrate their forces, we became more successful at what the role of the B-52 could really bring to bear, which is massive air power.
Our defense posture provides the umbrella under which all competition flourishes in this capitalistic society. So the B-52, because of its tremendous design, lasted a great long time. And because of the philosophy and sometimes the tendency to forget history, which we seem to do in this country, it's lasted a long time as well. It's had to.
During the protracted years of the Vietnam War, nose art adorned more than a few B-52s, reflecting the personalization and character that the crews added to the aircraft. Although nose arts were milder compared to its Second World War counterpart, the missions undertaken were no less perilous. B-52 crews faced the challenges of swift and nimble enemy MiGs, anti-aircraft guns, and, most menacing of all, deadly surface-to-air missiles. Despite these hazards, they pressed on with their mission, embodying the resilience of soldiers who carry out their duties irrespective of opposition. Post-raid, ground crews hastily repaired the bullet-riddled airframes of returning Stratofortresses, preparing them for the next mission. Sometimes, the hits were uncomfortably close. Despite the low fuel takeoff policy, the substantial weight of the bomb load placed considerable stress on the engines, necessitating regular maintenance and often replacements. To ward off MiGs, rear gunners played a crucial role, occasionally shooting down the agile adversaries. These gunners operated from their solitary outposts, utilizing a radar-aimed, remote-controlled array of 4 cannons with devastating firepower. The tail gunner's position was omitted with the introduction of the B-52G and H models. All B-52G and H models were equipped with EVS, electronic visual systems, representing a technological advancement enhancing their capabilities. This enables the pilot and other crew members to see what is ahead of the aircraft, even in darkness and fog, via infrared television cameras and a monitor. This development came just in time as the role of the B-52 had changed from that of a low-level tactical bomber. Today's Stratofortresses may find themselves flying through atomic clouds, with the B-52 shielded by radiation-proof curtains and the electronic visual systems becoming the crew's sole visual connection to the outside world. Despite the evolving mission, red phones and flashing lights remain the standard currency of the Strategic Air Command. When the bell rings, whether in exercises or during wartime, SAC's formidable deterrent force leaps into action. The first order of business for the operations general is to abandon the ground base for the safety and mobility of an aerial combat post. Simultaneously, as the alert is issued, aircrews swiftly converge on their aircraft, perpetually on standby for immediate action. The general takes to the air, with the B-52s following closely. It is only in the safety of the skies that SAC's deterrent force can endure an attack while simultaneously being en route to deliver a response. A high-speed takeoff is deemed essential for survival. In these exercises, preparations are made for the possibility of a nuclear flash, and radiation-resistant curtains are deployed. At this stage, the crew becomes entirely dependent on the EVS and other electronic aids, as looking outside the cockpit becomes too hazardous in the face of potential radiation exposure. Flying low over the ground, each pilot awaits his orders. During this exercise, the B-52s are recalled, yet everyone involved acknowledges their capability to enter enemy territory if the need arises. The exercise concludes, leaving the general satisfied. After nearly 40 years of dedicated service, the B-52 continues to fulfill its mission effectively. But it is evident that the aircraft is approaching the conclusion of its service life.
We went over their arc light, which was 6 months at a time. And I did it 5 or 6 times, I don't remember. But the thing was, is you live with these people, you live with them, you sleep with them, you eat with them. They become brothers, so you trust them with your lives. You literally did, because if an EWO said brake right or brake left, you didn't ask why, you just did it. That means turn a plane left or right because there was a threat coming. You just did it. You knew that whatever he was telling you, he was in the plane with you. And vice versa. You never second guessed the other guy because they were the expert in their position. And that's what the teamwork was. You learned to respect the other guy's position and how well they served the position. The B-52 is getting old. It does need a follow-on bomber. And I think the B-1 is probably that type of an aircraft. Next question evolves is, do we need the B-2s? I don't know. It's awful expensive aircraft.
Almost immediately after the initial B-52 rolled off the assembly line, the Strategic Air Command began the quest for a suitable replacement. The ill-fated XB-70 was an initial attempt, featuring an advanced design that became outdated due to the advancements in ground-to-air missile technology. More recently, there was a swing-wing B-1 bomber developed by Rockwell International. The B-1 offered a blend of high speed and altitude with its wings swept back, as well as more cost-effective low-level flying with the wings forward. The cost of deploying a large number of B-1s was deemed unacceptable to Cater administration, leading to the shelving of the project throughout the 1970s. However, in the 1980s, a revamped version, the B-1B, entered production. This time not in the high-altitude role, but as a low-level bomber. Approximately 100 B-1Bs were deployed by the Strategic Air Command. Although the plane comes with a hefty price tag, if the B-1B proves to match the overall performance and value for money that its predecessor, the B-52, clearly demonstrated, it would be considered money well spent. After about 7 decades of service, spanning a period of remarkable technological advancements, the B-52 still stands as a weapon of formidable power and effectiveness. It remains a challenging act to follow in terms of its enduring impact and capabilities.
This is the consolidated B-36 intercontinental bomber, sometimes referred to as the Peacemaker or the Big Stick. It was the largest conventional warplane ever built. It had tremendous range and a great payload. with its 6 piston engines turning, and later 4 more jets burning, the B-36 for many years projected America's military might.
It was a monstrous airplane. It had 6 engines, and they were pusher props. Now later on they hung jet pods on the ends of the wing, but the early models were all piston engines, pushers. It was a huge airplane, and it was designed then to carry atomic weapons.
But by the mid-50s, its sheer size, cruciform shape, and middling performance worked against it in a world of pure jets. However, in its heyday, the 36 was the very pinnacle of successful giantism. Rather surprising given that a decade and a half earlier, the United States had all but abandoned the idea of operating massive aircraft known as XBLRs, or the Experimental Bomber Long Range. The first attempt, the XBLR-1, resulted in the Boeing XB-15. This was an ambitious and useful experiment that demonstrated the importance of 4-engined bombers. The XB-15 carried a crew of 10. However, its 150-foot wingspan proved too large for practical use. But Boeing's next offering, the XB-17, which followed a year later, perfectly met the needs of the Army. Despite the Army Air Force's decision not to proceed with the XB-15, the political mood in 1938 was undergoing a sea change. With the acquisition of total power by the Nazi Party, American military planners had to contemplate a scenario of German domination of Europe, including Britain. In America in 1938, the question being secretly asked was, what if Britain did fall? Perhaps the only way of striking back at the Axis powers in Europe was with the once dismissed experimental bomber Long Range. The XBLR-2 came together as the XB-19, somewhat bigger than the XB-15, and in fact bigger than any other aircraft in the world at that time. It was to be built by Douglas Aircraft in California. However, by the time the B-19 first flew, the Battle of Britain had already been won, when a few hundred pilots of RAF Fighter Command were just able to halt the Nazi juggernaut. Notwithstanding these events, the B-19 project continued. Some indication of the project's size can be gained from the scope of its planning. The XB-19 required no less than 4 acres of drawings, 500 engineers, and more than 2 million hours of R&D and construction. The wings on their own had a 212-foot span and were over 1/10 of an acre in actual size. The wings also held 4 giant engines. Each one had more than twice the power of those on the B-15 predecessor. The B-19 even had its own hoists for changing the 16-foot propellers, and was able to lift its own massive engines on and off the wings. Each wing contained a lighted passageway, enabling crew to reach the engines in flight. The 2 massive main towers were 8 foot high, and each was of 24 ply, using 150 miles of rayon cord and 3 miles of steel wire. All of the flying control surfaces were so large that they could only be operated via power-assisted devices. The rudder alone took up an area of 237 square feet of movable surface. To communicate within such a large aircraft, it was necessary to install a 24-set telephone system and a loudspeaker cum fire alarm warning device. And to enable missions of up to 3 days and accommodate at least 13 crew, it was necessary to have a galley, a wardroom, as well as a bunkroom. Such were the proportions of what Douglas liked to refer to as their hemispheric defender. In theory, this behemoth flying machine could fly more than 1/3 of the distance around the world without refueling, perhaps reaching parts of Europe and the return trip too. On June 27, 1941, the B-19 made its first flight from Douglas Aircraft in Santa Monica to March Air Force Base. Despite various suggestions to the local press at the time, the B-19 was really a proof-of-concept aircraft to explore what could be learnt about building giant aircraft. The B-19 also presented the same problems and lengthy delays as Boeing had endured with its 4-year development of the B-15. Knowing that many of the lessons recently learnt were already becoming obsolete, Douglas suggested that the B-19 be abandoned. However, the Army remained firm that the XBLR-2 would be delivered. In fact, the Douglas Company's view may have been quite sound, as the war had necessitated that the 2 prototype long-range bombers be ordered 6 months before the B-19 ever flew. The Northrop B-35 and its competitor, the enormous consolidated B-36, would use whatever data could be migrated from Douglas. In fact, the B-35's design was a totally different concept, relying upon advanced flying wing aerodynamics to gain maximum range, an idea that was far ahead of its time. Nevertheless, it was the consolidated XB-36 which the Air Force adopted. It was a symbol of pure 1940s giantism, and likely would have benefited from some of the ideas incorporated in the B-19. However, it was a virtual flying gas tank, carrying with it all the fuel it needed for a there-and-back European mission. The Second World War had come and gone before Consolidated's giant reached production, and as Britain did not fall to Germany, the 36's absence had no impact on the conflict, although its presence became critical in the Cold War that followed. It was during this potentially cataclysmic test that America's peacemaker really came of age. The newly formed Strategic Air Command under General Curtis LeMay would regularly fly to far distant territories just to demonstrate its enormous reach. It was all a very effective show of force, although by the mid-50s, one that was starting to be questioned.
The airplane flew like a glider. It was easy to fly. Anybody could have flown it with 5 hours of stick time. It was a beautiful airplane. It's good that they never had to fly military missions, even with the 4 jet engines which were placed on later.
The success of an earlier Strategic Air Command gamble with the B-47 Stratojet medium bomber demonstrated the need for a faster swept-wing, all-jet-power heavy bomber. Yet Consolidated felt they could still provide a ready answer. The B-60 arrived after a standard 36 fuselage was married to swept wings and tail surfaces. It was propelled by 8 turbojet engines. The concept would have been economical, but advances in in-flight refueling made it no longer necessary for massive fuel loads to be carried. The age of giantism was coming to an end. Strategic Air Command wanted a smaller, faster and more sophisticated heavy bomber, and Boeing's B-52 Stratofortress fitted the bill. And in terms of years of service for dollars spent, the B-52 was able to adapt and evolve in a way Convair's Big Stick never could. Still, credit where it's due. The B-36 was for a number of years America's sole intercontinental bomber and served as an effective deterrent, appropriately earning the type its other nickname, the Peacemaker.
I am Lieutenant Colonel Schmidt from the Bomber Section of the Directorate of Aerospace Safety at Norton Air Force Base, California. You are about to see and hear a most unusual story about the aircraft you fly, a story that has made aviation history. We at the Directorate of Aerospace Safety believe the factors of this incident will increase your understanding of B-52 flight characteristics and heighten your appreciation of its capabilities. The aircraft involved was a B-52H on loan to the Boeing Company. Its flight crew members were Mr. Charles Fisher, instructor pilot, Mr. Richard Curry, pilot, Mr. Leo Kors, co-pilot, and Mr. James Pittman, navigator. Here to tell you this remarkable story firsthand is one of the Boeing pilots who was at the controls, Mr. Richard Curry. Dick?
Thank you, Colonel Smith. Our mission was to conduct a flight load survey to obtain and record the structural loads encountered on a routine low-level sortie. Special instruments were installed in the cockpit to record the stresses exerted on various parts of the aircraft. An 8-hour flight was scheduled along a route running from Wichita, Kansas, southwest to the Rocky Mountains. The mission called for 10-minute runs at 280, 350, and 400 knots calibrated airspeed, at 500 feet above the ground, utilizing the low-level mode of the autopilot. The initial portion of the flight progressed as planned, with only light turbulence encountered at the end of the 6th leg. However, as the aircraft turned north in the vicinity of Wagon Mound, New Mexico, and began a course parallel to the mountains, the instruments, identified here in orange, began indicating increasing turbulence and heavy gust loads on the tail section. We elected to discontinue the low-level portion of the flight, and the aircraft was climbed to 14,300 feet mean sea level, where the air was relatively smooth. We then decided to continue the mission using the next speed schedule of 350 knots. Since the terrain elevation was steadily increasing, the aircraft flight path was approximately 1,000 feet above and slightly to the right of East Spanish Peak near Aguilar, Colorado. Wind at this time indicated 62 knots west component, but no turbulence was noted. Then at 345 knots, while accelerating to 350 knots, an area of extreme turbulence was encountered. It lasted approximately 9 seconds. With this model, I will attempt to show you approximately what happened to the aircraft when it was struck by this turbulence. The turbulence came in rapid, explosive-like gusts. The airplane was pitched up and yawed to the left, followed immediately by a very rapid yaw to the right and a resultant right rolling moment. This motion was opposed with approximately 80% left wheel authority. A high-frequency vibration was felt in the rudder pedals, and rudder pedal displacement gave no response. The elevator response was also very poor. The crew was alerted to prepare to abandon the aircraft. However, we soon realized that the aircraft still had marginal control. At this time, the air brakes were raised to position 1 to improve longitudinal stability, and a fuel transfer was started to maintain a forward center of gravity. Lateral control was aided by very small asymmetric power settings, which helped maintain the aircraft in a side-slipping flight attitude. After the aircraft was brought under marginal control, we called for assistance. The first to arrive was a Boeing XBLR-1. This is what the pilots saw. Approximately 83% of the vertical fin had been ripped away. We immediately set a course for Wichita, Kansas, and developed our flight strategy. Boeing Flight Test had already recommended that the aft main gear be lowered, as this would be a stabilizing factor in the absence of the vertical fin. Any drag after the center of gravity would tend to stabilize the aircraft. Here the outboard air brakes are at position 4, which is also an area after the center of gravity. Here our airspeed is about 210 knots indicated, which is about 30 knots above the minimum recommended for this weight with flaps up. Small excursions up to 220 and down to 200 knots were made. However, 210 knots was found to be most satisfactory. At this time, the altitude was approximately 12,000 feet mean sea level. The center of gravity was calculated to be about 19%, with the vertical fin missing. The weight of the vertical fin is estimated to be about 2,000 pounds. Due to the reports of unfavorable weather at Wichita, it was finally decided to divert us to Blytheville Air Force Base, Arkansas, where surface winds were more favorable. While in the Blytheville area, making preparations for landing, we were advised to extend the tip protection gears first. Then the forward trucks were lowered. A yawing oscillation occurred during forward gear extension. However, this ceased when the gear reached a down and lock indication. We reduced airspeed to 160 knots at 10,000 feet and prepared for a long, flat final approach, hoping to be able to flare and touch down at the same speed. 160 knots flaps up approach speed was selected in order to obtain optimum body angle. We had computed a no drag chute stopping distance of 5,000 feet. Here is the aircraft on final approach. 160 knots, outboard air brakes at position 4. All engines are near idle. Crossing the threshold, still at 160 knots, the aircraft started a slight left drift, and we decided not to hold off any longer, but put it on the runway. At touchdown, all air brakes were raised to position 6. We elected to use the drag chute, but decelerated to 130 knots before deploying it. We considered the possibility of a go-around, and had it been necessary, we would have used outboard air brakes at number 6 position. This is the B-52 at Blytheville Air Force Base shortly after landing. This aircraft was flown 5 hours in this configuration from the scene of the incident over Colorado to Wichita and then to Blytheville Air Force Base, Arkansas. A portion of the aircraft's original mission was to record the gust loads found in moderate turbulence. However, the loads we encountered were much greater than had been anticipated. An analysis of the recorded information revealed gust loads of a greater magnitude than had ever previously been recorded on any large aircraft. Well, Colonel, I guess that about sums it up.
Thank you, Dick. We at the Directorate of Aerospace Safety are indeed grateful to you for bringing us this first-hand report. A review of the data collected on this flight indicates that the airframe design criteria for future heavy aircraft should be reevaluated and possibly revised for future aircraft design. An engineering change to incorporate additional strength in the B-52 empennage is well underway at Wichita. In conclusion, let us review the things which enabled this aircrew to return this aircraft to a safe landing. Excellent crew coordination to regain positive control of the aircraft. A call for chase aircraft. A call for expert technical assistance. Reduction of airspeed to 30 knots above minimum recommended, flaps up. Proper use of air brake settings with inboard air brake circuit breakers pulled. Transfer of fuel for better aircraft stability. Extension of the aft main gear only for directional stability, and judicious use of throttles for desired power settings for optimum controllability. We salute this Boeing flight test crew for a fine job of airmanship. By bringing this aircraft back, they have supplied the Air Force with invaluable data on the gust load velocities that are often imposed on large aircraft flying low-level missions. Salutes also to the other agencies and the Boeing Company for their excellent cooperation.
No two nations on Earth are any longer cut off from each other by geography. We all live at the edge of the same ocean, the air ocean which envelops the globe. And in the air age, geography has new meanings for the safety of the American and Canadian people.
The shortest route from the USSR, which was the prime antagonist in the Cold War against the USA, was over the Arctic. There's no other fastest route. And unfortunately for Canadians, when you looked at it, we're right in between these two forces that were saber rattling and causing a lot of grief for each other. So it was natural that's where they would put it. And they wanted to be as close to Russia as they could be in order to get as much warning as they possibly could.
This was to build, with the cooperation of Canada, a radar early warning line north of the Arctic Circle. Starting at the northernmost tip of Alaska, it would stretch 3,000 miles across the continent to Baffin Island, opposite Greenland. Distant Early Warning Line, they named it. DEW Line, it became.
DEW Line was a string of radar stations that ran about 3,200 miles across the Arctic, about 200 miles inside the Arctic Circle. And there were 6 main stations where you might have about 50 to 80 people. There were 25 auxiliary sites where you might have up to 20 people. And then in between all of those stations were what were called intermediate sites, or I sites.
In this grim and forbidding Arctic waste, a top priority defense project is being rushed to completion. Known as Operation DEW Line, DEW for Distant Early Warning, it is the construction of a string of radar bases. Building in these frigid latitudes becomes a test of men and machines. Almost every type of terrain is encountered, from ice hundreds of feet thick to Arctic tundra.
If I remember correctly, it was around $500 million to build, which back then would be a lot of money. You can do the inflation corrections for today's dollars and cents. And it took about, I think it was around 20 or 30 months to build. So it was really an incredible engineering and construction feat.
The thickness of the ice must be tested for landing strips, and radio towers must withstand howling Arctic gales. On a tour of inspection of top secret bases, U.S. Secretary of Defense Wilson is joined by Defense Minister Campney and Defense Production Minister C.D. Howe of Canada and other members of the Joint Commission. The vast undertaking will cost $500 million and take 2 years to complete. These watchdogs, stretching 3,000 miles across the Arctic, are the price North America must pay for security. They will sound the first alarm should an air attack come.
The mass movement of supplies was done during the summer months, where they had the sea lift, and they would do that both on the east and west coast. And then there was continual resupply during the winter months by aircraft coming up from both Montreal, Winnipeg, and Edmonton as well. So there was always what was called a vertical flight, which was the flight up, and then the lateral flights were the ones that went across the line. Generally, we'd get a plane once a week if weather held. Sometimes weather didn't hold.
The Arctic. Desolate, savage, remote. A wilderness of unending barren vistas. Through most of the year, locked in bitter cold and almost endless darkness.
The weather in the Arctic, I can sum it up in one word, which is cold, or 2 words, which is bitter cold. In the wintertime, certainly -40 was not uncommon. And you could take a glass of water outside and throw it up, and it never hit the ground. It just evaporated into vapor. It was so cold. So generally, cold is the word. And in fact, once I froze to the point where I was actually praying that my feet would freeze and stop hurting because I was so cold. I was in a plane that I couldn't get off of.
In the camps of the construction contractors, living conditions were primitive, but already the crews were changing the face of that far north country. The Eskimos too were recruited, and they did a good job.
Dark for most of the winter months, and in the summer months, 100% light. And I used to actually have to nail a blanket up over my window in the summer months in order to simulate darkness so I could go to sleep.
Often the expression snowed in had a completely literal meaning. But nature in the Arctic no longer seemed so savage, for life on the DEW Line had become pretty civilized.
Inside the buildings, life was good. We were very well fed. In fact, I gained 30 pounds on my first stint up, and the clothes that I had to wear to go south wouldn't fit anymore. So I actually sent away to Sears and mail order and bought a three-piece suit with 2 pair of pants and a television set for $29.95. I lied about the TV set, but it was $29.95 for a three-piece suit of clothes so I could actually have something to wear when I went out. We're well fed. We got movies generally when the planes arrive. We get about 2 to 3 movies a week. Some of them were first run. If you were stationed at a site, you would have a room of your own, about a 6x9 room. So it was fairly comfortable. If you were transient, which I was for a lot of my time, you simply got whatever you could. But I primarily slept inside the buildings. I didn't have to sleep outside, which some people did. We had what are called at-will tents, and they would sleep outside. That got rarer and rarer as time went by, and we'd try to house people in transient quarters.
Spring baseball practice started early. While you were working up an appetite, the chef would be doing something about it. After dinner, it was each man to his own pleasure. It might be music. Perhaps you preferred a rousing game of table tennis, no quarter given. You could curl up with a good book. Or there was that other fine intellectual pastime called poker. No quarter given here either.
There was a sense of we're all in this boat together. But what you really had was a group of nomads all sort of clustered together. And when you consider that when you were on your shift or doing your duty roster, you were on with one other person. Now, he'd be watching the radar while you're looking after the equipment and vice versa. So you didn't even really get a chance to chat with that person for any extended period of time unless you wanted to. So what you had on a station of 15 was probably 14 loners. And one social person was going crazy trying to find somebody who would talk to him.
What if someone at Civil Defense pushed the right button, and this is not a practice alert, but warning of a real enemy attack? And if it is a real attack, how will the United States cope with it? The answer begins thousands of miles to the north, at the dew line, the distant early warning system, a network of radars which stretches some 5,000 miles.
It was certainly sobering. You had a sense that not so much that you were leading edge in terms of technology, but you were certainly leading edge in terms of what was happening in the world. And you also recognized that you were a very thin line between letting people know that the end was going to be coming. And to that end, it really did cause you to take the job very seriously. Things were very tight. On one case, if you ever missed a plane, there was no what happened, it was just goodbye. You just got put on a plane and sent south. You did not fall asleep at the console. That was the kiss of death. People took that very seriously.
Immediately upon detection, the information would be flashed to the Combat Operations Center of NORAD, the North American Air Defense Command, buried deep in the heart of Cheyenne Mountain near Colorado Springs. NORAD's mission is to defend Canada and the United States against aerospace attack.
Our reporting process was that on every council there was a message sender, and we would dial in the information. Whenever we saw a plane come down, we would do 2 or 3 paints on it in order to get the direction and speed. And we were never told what was coming. I mean, they would know. And so we would report it, and then if it was a known aircraft, they would say it's Scandinavian 935 and continue to track. If it was an unknown, they would say unknown, continue to track every 3 minutes. And we would send reports in every 3 minutes. Those reports went to the main stations, from all the outside stations into the main station. Main station would have direct communication with NORAD down in Cheyenne Mountain.
When the unknowns enter the NORAD area of responsibility, the Commander-in-Chief, NORAD, will declare an air defense emergency. And United States and Canadian long-range fighter interceptors will be launched. First, to identify the aircraft, and, if found hostile, to destroy them.
Basically, our job would have been over in about 30 minutes, because that's about the time it would have taken from a fairly fast aircraft to go from the top of the radar scope to the bottom. So as soon as we picked it up, which might be a couple hundred miles out, and we painted 2 or 3 paints on the screen, we then knew the speed and the direction. and that would be reported. And if it was an unknown, they would continue to track it. They would try to identify from all the sources that they knew, where this aircraft come from. It wouldn't be one aircraft. I mean, in my mind, it would have been a whole series of them coming down. So you would have seen all kinds of them right across the line. And then after they went off the bottom of the scope, that's it. Our job was done. We had raised the flag, gave them the call, and basically our hope is that someone would come and get us and take us out of there.
By order from the White House, you are authorized with the decision made. The United States will now strike back with a counteroffensive unparalleled in the history of war. Airborne bombers of Strategic Air Command will be ordered to take full reprisal against the enemy's homeland. Others will roar off to the attack from thatch bases located around the world.
Cuban Missile Crisis was, first of all, for me, the most exciting time up there. We recognized the darkness on the horizon. Frankly, a lot of us didn't think we were going to come home from there. We felt that we would get left behind. We doubled up on the consoles. I mean, we watched both of the upper and the lower beams, which where normally we would only watch the lower beam. And there was increased activity by the Strategic Air Command. We were sending the emergency action message, which is basically the fail-safe message, on a much more frequent basis. So we had our finger on the pulse while watching what was happening. It was tense and interesting.
The missile age is here. A new and grim challenge to the free world. A challenge to our very survival. We must keep ahead of communist efforts to dominate the world. We must have missiles of all types for all purposes, to protect our own country, to protect the free nations of the world, preserve peace.
The major turning point was the intercontinental missile, and they did incorporate the dual line into what was called the BMU system, which is the ballistic missile early warning system.
While still thousands of miles away, the missiles would be detected by BMUs, the ballistic missile early warning system. Instantly, BMUs would flash the warning to NORAD and to MAR, indicating the speed, direction, and number of attacking missiles. MAR would then detect, track, and identify the real warheads from the decoys in microseconds. At the proper moment, Zeus would be blasted from its silo.
And we basically became a communication channel between those two sites. That's probably the biggest thing that caused it to die. Also nowadays, a bomb in a box is much more threatening than something coming over the pole. Certainly submarine-launched missiles are going to get you within 18 minutes or so.
But perhaps the true historical role of the DEW line will prove to be the opening up for peaceful and productive purposes of a vast new frontier above the Arctic Circle, the untapped resources of which we have as yet barely glimpsed. That would be the finest reward of all for the men who built the DEW line.
There's a lot of Cold War history around. I think that I'd like to see it remembered as probably a group of hardy folks that were in the coldest part of the Cold War. It didn't get any colder, and there was no Cold War down south. We were up there as that thin line of people between the Russians and the Americans, hoping to give people enough notice to do something should the disaster happen.
The F-100 is one of our primary tactical support weapons systems. This aircraft has a proven history of outstanding performance. One of the reasons for this dependability is the rugged power plant. For one, a high-performance aircraft is adaptable to many missions. It is used for reconnaissance, as a tactical fighter, and as an interceptor. Approximately 30,000 pounds of thrust is developed by its twin engine. The F-102 is the first operational airborne delta-wing aircraft. Performance characteristics of this weapon system are ideally suited for intercept missions. A reliable power plant is essential for the success of any mission. The F-102, 101, and 100 are all powered by the rugged J-57 engine developed by Pratt & Whitney. The individual engines vary somewhat, but for the most part are the same fundamental design. The J-57 is a dual compressor engine. The engine consists of the following components: the inlet, the low-pressure compressor, the high-pressure compressor, the diffuser case, combustion chamber, the first, second, and third stage turbines, the afterburner, and the exhaust nozzle. The low-pressure compressor, referred to as N1, is driven by the second and third stage turbines. The high-pressure compressor, N2, is driven by the first stage turbine. These two units, or spools, are not mechanically connected. The J-57 operates on the same basic principle as all jet engines. Pressure, presented in graph form below the basic engine outline, and velocity are increased by a series of rotors in the compressor section. A compressor bleed system prevents compressor instability when the engine is operating at reduced power. The compressed air passes through the diffuser into the combustion chamber, where the air expands, thus reducing somewhat the velocity and pressure. Fuel is mixed with a portion of the air to form the combustible mass. When combustion occurs, the gases are expelled through the turbine. At this point, power is extracted by the turbines to drive the compressor. The remaining energy, expelled through the exhaust nozzle, provides the thrust. Since exhaust nozzle and turbine discharge pressures are relative, turbine discharge pressure is used as a parameter to determine thrust. Thrust is the measure of force developed by the engine. Force is determined by mass times acceleration. Mass is the weight of air and fuel passing through the engine. Acceleration is the difference between inlet and turbine discharge velocities of this mass. But thrust may be expressed by the formula force equals mass times acceleration. The engine trim charts are based on this formula. Additional thrust is obtained in the afterburner by increasing mass and acceleration at that stage. The basic engine pressure ratio during afterburner operation is maintained by increasing the exhaust nozzle area. Efficient engine operation depends on correct fuel schedule. The basic components of the J-57 main engine fuel system are fuel pump and fuel pump transfer valve, fuel control, and the pressurizing and dump valve. The fuel pump is a dual-element per-gear pump. One element supplies fuel to the afterburner, the other to the main engine. The fuel control meters the fuel required to operate the engine through its full range. The pressurizing and dump valve supplies the main engine fuel manifold and drains the manifold at engine shutdown. At engine start, fuel enters the pump through the impeller where the pressure is increased. This provides a positive pressure head to the main stage. At this stage, the fuel reaches output pressure. The pressurized fuel closes the fuel regulating transfer valve and the afterburner check valve and flows into the fuel control. The main metering valve is closed at this time. A portion of this fuel passes through a minimum flow orifice through the signal line to the P&D valve. Since the control is in bypass, pressure does not build up enough to close this valve until the power lever moves from cutoff to idle. When the power lever is moved to the idle position, the fuel dump valve closes. The main metering valve opens. The cutoff valve moves off its seat. The pressure loading valve opens. The P&D valve inlet check valve opens. And the fuel is supplied to the primary side of the fuel manifold through the pressurizing and dump valve. At approximately 74% RPM, the fuel pressurizing valve will open to supply fuel to the secondary side of the fuel manifold. The J-57 engine uses the primary and secondary system in order to obtain the highest possible fuel flow with the shortest possible flame. At low RPMs, only the primary side is used. When the emergency system is selected, the actuator positions the pilot valve to direct pressure to the shuttle valve system. The shuttle valve blocks off metered flow and provides support for unmetered fuel to the emergency throttle valve. This mechanical valve controls the flow of fuel. The afterburner element of the fuel pump will supply fuel to the engine in the event of main element failure. The primary function is to furnish fuel for the afterburner. The other components of the J-57 afterburner system are the afterburner fuel control, exhaust nozzle control, igniter valve, and the mechanical shutoff valve. The relative position of the components varies according to engine model. The afterburner fuel control meters fuel to the AD spray box. The exhaust nozzle control directs compressor discharge air to open and close the nozzle. The igniter valve injects fuel into the combustion chamber, creating a streak of flame to ignite the afterburner. In the event of electrical failure, the mechanical shutoff valve will terminate AD operation at approximately 80% RPM. Rotation of this valve causes AD stage fuel to bypass through the AD fuel control regulator valve. The fuel control unit is carefully calibrated on the test bench to assure accurate engine fuel schedule. The main functions of the fuel control are to maintain acceleration schedule below compressor stall zone, to prevent over-temperature during acceleration, prevent lean die-out during deceleration, and to maintain any selected engine speed within operating limits, regardless of altitude. The fuel control senses engine RPM, inlet temperature, and burner pressure to supply the correct amount of fuel for any ambient condition. When calibration has been completed, all external adjustments, except the idle and military trim screws, are sealed. These seals are installed to protect test bench precision calibrations and must not be removed. The J-57 engine will provide relatively trouble-free operation when all systems are functioning correctly. However, the systems must be properly rigged and adjusted. One of the most critical engine adjustments is the rigging of the fuel control linkage. Full range movement is obtained only when the fuel control and afterburner mechanical shutoff valve levers are correctly positioned. The levers are set to predetermined angles. A protractor or etched template is used to set the linkage at these angles. The protractor is positioned at the oil pump and accessory housing plug to establish a reference angle. This reference angle will be used to adjust the fuel control lever. With the fuel control lever in cutoff position, the difference between the reference angle and this reading must be the number of degrees specified in the tech manual. It may be necessary to readjust the fuel control lever to obtain the correct angle. The fuel control lever and serrated spacer are ratcheted to give the desired angle. The fuel control position, which, when all other linkage is connected, will close the afterburner mechanical shutoff valve. The power actuating rod is then attached to the fuel control lever. Move the mechanical shutoff lever to the detent position. The rod, connecting the cross-shaft lever and mechanical shutoff valve lever, may have to be adjusted to the specified length. The AD mechanical shutoff valve is held in detent position, while the lever is ratcheted to the position where the rod, which has already been adjusted to the specified length, will fit. Then all connections are tightened. Either the protractor or an etched template is used to again check the angle of the fuel control lever. It may be necessary to readjust the fuel control lever to obtain the correct angle. After corrections are made, all connections are then safe. Replacement or adjustment of most components will affect engine operation. Prior to aircraft installation, the engine is thoroughly inspected and tested to ensure satisfactory performance. A fuel leak check is imperative before initial start of a repaired engine. With the system pressurized, check all fuel lines and connections. The exhaust nozzle opening must also be rechecked before initial engine start. Nozzle diameter not within specified limits will affect engine efficiency. On some engines, a fail-safe device is installed to prevent total loss of power in the event of linkage failure. The device will position the fuel control lever to a 45-degree angle setting, which will provide approximately 90% RPM, thus ensuring sufficient thrust to maintain flight. After installation in the aircraft, all airframe to engine connections must be checked and adjusted, and the engine retrimmed. Final trim, to compensate for aircraft installation losses, is preferably accomplished with the aircraft headed directly into the wind. Prevailing wind velocity and direction must be within limits specified in the tech manual. The trim pad area must be free of loose objects that could damage the engine if ingested. To effectively trim the engine, power control settings must be coordinated. Throttle linkage is operationally tested before making fuel control adjustments. Movement of the fuel control quadrant must synchronize with throttle movement. Power control movement is transferred to obtain predetermined fuel control settings. The aircraft manual indicates the relative degree of movement throughout the entire throttle range. Close attention to detail is required when trimming an engine. Changes in ambient barometric pressure and temperature will affect engine performance characteristics. True barometric pressure and correct temperature, both recorded within 15 minutes of the trim run, are used to determine target CP7. Target CP7 is obtained by tracing the temperature and pressure coordinates on the trim chart. Start engine is specified in the tech manual and allow engine and exhaust gas temperature to stabilize. Required throttle to idle setting. Desired idle speed is obtained by adjusting the idle trim screw. As in all fuel control adjustments, final trim is always in the increased RPM direction. Proceeding with the trim operations, slowly advance throttle to military power. Allow 5 minutes for stabilize. Caution, do not overspeed or overtemp engine during run-up and stabilization. With throttle set at military power, record RPM, EGT, and the turbine discharge pressure, ET7. If ET7 reading is low, return throttle to idle and readjust maximum RPM setting at the fuel control. Turn the adjustment clockwise to increase RPM in order to obtain target ET7. Advance throttle to military power. Stabilize, then recheck ET7. Return throttle to idle. Check EGT and RPM. Make certain that RPM is within 2% of data plate speed indication. At the completion of the trim run, follow standard shutdown procedure. Accurate troubleshooting depends on a thorough understanding of the J-57 engine and its system function. Only by correct analysis of the interrelated parameters can the malfunction be isolated. Proficient troubleshooting is the mark of quality. The Tech Manual outlines the common symptoms of engine malfunctions, the probable causes, and their remedy. Basic parameters used to determine engine performance must also be considered when analyzing problems. These basic parameters are RPM, ET7, and EGT. One of the most detrimental engine malfunctions is overtemping, or high EGT. Perform static checks of ET7 lines and connections, and the exhaust nozzle opening. Make sure the anti-icing valves are closed. Then check for instrument accuracy. All static checks have been performed and found satisfactory. Now the engine must be checked for proper trim. As engine approaches military power, check exhaust nozzle for creep. Check to make sure the ET7 has not exceeded target, and RPM is within data plate limits. If high EGT still exists, the engine must be removed and a hot section inspection must be performed. Inspect the burner can for cracks or hot spots. Check fuel nozzle for loose, burned, or missing air caps, and evidence of fuel leaks or clogged air holes. Check the first stage turbine nozzle guide vane for excessive flow. Turbine vanes flowed beyond limit will distort the gas path, causing loss of turbine efficiency. The amount of fuel required to compensate for this loss accounts for the excess temperature. In conjunction with correction of the bowed nozzle guide vanes, or providing they were within limit, additional checks are necessary to assure the problem is correct. Inspect first and second stage outer air seals for cracks, burned areas, and damage to outer knife edges. Check clearance between outer air seals and turbine blade shrouds. Check first stage turbine dislocating dimensions. The cause of high EGT may have been one major problem isolated at any phase of the investigation, or the accumulation of minor deficiencies requiring several procedures to isolate and correct. As RPM exceeded data flight limits during initial high EGT troubleshooting trim runs, the engine would have to be seal cleaned before proceeding with other checks. This process is intended to restore compressor efficiency. When this operation is completed, retrimming the engine may bring all parameters within limits. When troubleshooting engine performance deficiencies, it is necessary to consider all three parameters: EGT, RPM, and PT7. As an example, failure to obtain target PT7 can be caused by many things. By comparing the relationship to EGT and RPM, many unnecessary troubleshooting steps can be eliminated. For instance, when all three parameters are low, a fuel scheduling deficiency is indicated. First, check for full travel of the power lever fuel control quadrant. Military position must not be less than 54 degrees. The next step is to remove the fuel control and check the position of the camshaft. With the camshaft cover removed, lever positioned at 11 degrees, and the temperature sense bulb in a 60-degree Fahrenheit bath, measure the distance from the end of camshaft to the cover flange. This reading should coincide with that on the camshaft depth plate. Tolerances and replacement instructions are included in the engine tech manual. The engine tech manual includes specific instructions for maintenance procedures. These manuals represent a vast accumulation of knowledge and experience. Through individual ability, initiative, and constant use of the tech manual, proper maintenance and troubleshooting procedures can be achieved. This is the goal of the Improved Maintenance Program.
Aviation, the art of aeronautics, began with the dreamers, inventors and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.